Okay. Hi, everybody. Thanks for the invitation to talk to you today about ClimaSG, which is a weather generator for crop modeling and water requirement studies that we have developed at the IAS, which is the Institute for Sustainable Agriculture from the Spanish Research Council. Although I do my teaching in agronomy at the University of Córdoba, so programs like the one that I'm presenting here is both related to research, but also to my teaching in the undergraduate class. Well, we are not talking about a new weather generator, but just a modification of SIMMETEO that had three main objectives. The first is to reduce the problem of over dispersion in rainfall data. In other words, the typical reduction in interannual variance in rainfall amounts. Also, try to add new weather variables which are required for the calculation of evapotranspiration when using combination equations, which are wind speed and vapor pressure. And third, to simplify the acquisition of input data. Basically, for education purposes, many times we need to be able to access to weather data in different parts of the world. And to facilitate the students with that, we thought it would be nice to include the database of CleanWatt from FAO that has more than 4,000 weather stations and provides the monthly values which would serve as input data for the program. The problem of over-dispersion is the general underestimation of interannual variance in monthly and annual total rainfall, although it has also been observed for temperature. This phenomenon is related to the predetermination of interannual variability by the model of rainfall occurrence. For instance, in SIMMETEO and its parent model, which was WGEN, the rainfall occurrence is simulated using a first-order Markov chain, and that may cause over-dispersion. The idea is that when we have, when we compose the distribution of monthly rainfall, where the mean of the distribution would be the product of N, the number of days in the month, by P, which is the mean rainfall per wet day, by F, which is the fraction of wet days. We will also have a variance for monthly rainfall, which is given in this equation, where the variables to consider are, apart from F, N, and P, we have also the variance of rainfall per wet day. So if we use a given distribution for calculating rainfall, the occurrence of rainfall, that will determine the variance. In this specific example, or in this specific equation, D is the difference between the two transition probabilities that are used in first order Markov chains, which are the transition probability from wet to wet day, PWW, and the transition probability from dry to wet day. There was a very interesting paper by Shugen and Penin de Vries in '86, I think it was, that showed that those transition probabilities are related to the mean frequency of wet days in a month. They showed that for many locations around the world. So if we use these equations of Shugen and Penin de Vries, we come up with this simplified equation for calculating the variance of rainfall. So in the end, when we use a first order Markov chain, we will have a variance of monthly rainfall that can be calculated as a function of the frequency of wet days and the mean rainfall per wet day. And that's it. Then the variance of the annual rainfall will be just the sum of the variances of the different months, as we normally will simulate rainfall independently for each month. We don't consider any type of association of dryness or wetness between the months of a given year. This problem of over-dispersion leads in general to an underestimation of the actual variance. If we call that V to the square, then we need to add an additional variance, B2 minus sigma 2 sub annual. In other words, we need to add variance to the one that we can get using the Markov chain. How can we do that? Well, simply by adding a low frequency component to the simulation of the rainfall data. How can we do that? Simply, every year, what we do is that we simulate the actual frequency of wet days using this variance sigma squared sub f. To apply or to calculate this additional variance, what we need are actual values of annual rainfall variance. And that can be taken from a gridded monthly global precipitation data set like the one of NCAR, which has a 0.5 degree resolution. So we have used that climatology to determine for each pixel around the world, for each location, we can have the actual variance, interannual variance of rainfall. And with that, we can correct the simulation or the generation of rainfall data. Although we had a secondary correction as compared to SIMMETEO, which is trying to match the temperature range and RS. As you probably know about the model of Hargreaves that relates solar radiation to the range in temperature, to the difference between maximum and minimum temperature, you know that when we do generation of weather data, in this case with SIMMETEO, we have independent generation of the temperatures and solar radiation. And we try to associate the generation of the Tmax, Tmin, and solar radiation. I'm not going to stop at the equations, but I will go to more interesting aspects like the generation of the additional variables, vapor pressure in the first place. And what we do is to assume that mean daily vapor pressure is proportional to saturated vapor pressure at minimum temperature. To convert this ES at the Tmin, what we apply is a coefficient, and the coefficient is calculated using monthly coefficients. In this case, would be the monthly mean vapor pressure, that is the only additional input for the weather generator, divided by ES at minimum temperature for that month. Finally, for wind speed, we use a Rayleigh distribution, which has the main advantage that depends only on the average value of the distribution. So we can generate daily values of wind speed using this equation, where U sub M is the mean monthly wind speed, and then R would be a random number from the 0-1 uniform distribution that would generate the values of U for each day of the month. We have tested the weather generator first comparing with actual weather data sets. And first, we try to make a comparison for rainfall at temperature with a lot of weather stations taken from the NOAA database. And we use as selection criteria all those locations that were already in the data set of CleanWatt and had more than 90% of the data in the period from 1988 to 2017. We found 547 stations that met those criteria, and we use them for checking the distributions of rainfall and temperature between the actual and the generated using ClimaSG. We collected also data from completed stations that had, apart from temperature and rainfall, had solar radiation, vapor pressure, and wind speed. And we collected data from 45 stations in Spain that had around 15 years of data from the CR system. That's the central government of Spain that runs that system. And we took also data from California, around 30 years, from 13 stations from CIMMETEO, taken from different counties all around California. Then we tested the generated data for their quality for crop simulation. And to do that, we use OliveCan, which is a crop growth and yield model of olive orchards. And we tested that only in areas where olive is grown actually. So we only took some of those in Spain, so only less than half of the stations in Spain and only 3 in California where olive could be found. Finally, we did a test for the calculation of ETO using all the completed stations, 45 in Spain and 13 in California. Well, the results were more or less satisfactory in the fact that for temperature generation, the quality or the problems were still the same that we can find in SIMMETEO. In other words, we can have problems with minimum temperatures because the evaluation of the standard deviation of temperatures might be off in many locations, but the quality parameters are quite the same as in SIMMETEO. But we did not change basically the generation of temperature, so this had to be expected. But in the most important thing, which is the over-dispersion problem, here we have the evaluation of the standard deviation of monthly rainfall comparing SIMMETEO that has an intercept of 3.1 and a slope of 0.66 and a mean bias error of minus 8.8. That indicates that the standard deviation of monthly rainfall is in general underestimated in most locations around the world. On the other hand, ClimaSG had an intercept close to 0.06, a slope very close to 1, and an R-square of 0.78. The mean bias error was now very, very low. So we feel that the objective was perfectly accomplished in correcting the variance of monthly rainfall and therefore seasonal rainfall. In the case of ETO, the success of ClimaSG was also quite remarkable. Here we have statistics for actual ETO in the month with higher evaporative demand, which is July in California or Spain, and the actual values of the mean ETO in Spain is 655, for ClimaSG 6.6, and the standard deviation, which is quite important for us too, 1.1 versus 105 in ClimaSG. So we not only could reproduce the averages, which would be a minimum condition, but we could also reproduce the standard deviations of ETO in the months of higher demand. The root mean square error for the ETO in the month of July were very low, 0.3, 0.45 for Spain and California, and for the 95% probability level for daily ETO, 0.68 and 0.6. The point is that we can not only get average values, but also we can have a very accurate estimate of the maximum values or 95% values of ETO, which are important to determine the peak demand for the crops, which are required for design of irrigation systems. The main conclusions about testing the weather generator are that the problems with extreme temperatures are still there, because they are the same as with SIMMETEO. That the generation of wind and vapor pressure was satisfactory. Rainfall variability has improved over SIMMETEO with ClimaSG. That the generated ETOs are statistically equal to actual values in Mediterranean type climates as the one that we have tested the model with. We have had problems with long runs with olive that may suffer from extreme low generated temperatures. In the case of olive can, when we have a very low temperature, we can have defoliation by frost. And when we are doing a very long run of many, many years, then a given frost problem will take several years to be corrected by the simulation. So that's a problem with long-term simulations in trees. But in trees, we can also work in static mode, and in that case, the generated data would be fine, because the orchard characteristics are reset every year. The program can be downloaded from the webpage of the University of Córdoba. You can see, well, if you look and you Google ClimaSG, then you can find it easily and can be downloaded. It's a standalone single program developed with Visual Basic, Visual Studio 2019, I think. And we have versions in English, Spanish, French, and Portuguese, and there are tutorials also available. It just needs to, the user opens, selects a country, and it will show the different stations for that country, selects one station, and then the user may perturb the series by adding temperature or changing the rainfall in a percent. We can use the same value for all months in the year, or we can change differently the different months in terms of temperature or rainfall. We select the number of years to generate, and then we just click and get the generated values. We will have also an analysis. The program will provide a rapid analysis of the time course of ETO, average temperature, rainfall during the year, and the frequency distributions or the time distributions of the probability of frost in the autumn, the first frost in the autumn, or the last frost in the spring. Apart from that, we can, apart from using data from the CleanWatt database, we can add new stations using this form. We can start from a given location and change only the maximum or the minimum temperature or the rainfall or whatever. The generated data has two formats. We generate two files. One is the format that we use in the 3 simulation models that has all these variables for the maximum, minimum temperature, rain, wind, vapor pressure. And also we recently incorporated DSSAT format because it could be handy for some people working with DSSAT. Thanks for your attention, and I'll be happy to answer any question that you may have.
Very good, Francisco, very impressive. I like what you've done. So I'll remind everyone, we're going to have a breakout session with him at what time? 10 o'clock? Yeah.
Do you want to hold questions till then?
Yeah, I mean, some general question for people who cannot make the breakout. But detailed question, please hold until the breakout. But any general question? No.
Let me ask one question. Francisco, can you hear me?
Yeah.
This is Okan. You mentioned that you are using the Markov chain.
Excuse me?
First order Markov chains, right? In your simulations. And there was the probability of differences between wet, dry days.
Sorry, I could not understand your question.
The question is, you are using probability of the difference between number of dry days and wet days, right?
Yeah.
If I correctly understand.
Well, we are using a first order Markov chain where you, depending on the status of the day, if it is dry or wet, you use a different transition probability to move to the next day. So in fact, that creates kind of sequences of rainy days, you know, they tend to cluster in spells, rain spells. So.
Yeah, my question is how you are getting those estimates? Because you are
the estimates of what? Of the transition probabilities are calculated just thanks to Shugen and Penning de Vries. They obtain a general relationship. Let me show you. Yeah, here. Well, here. This transition, can you see my screen?
Yes.
Okay, here PWW and PDW, these transition probabilities are just a linear function of F, which is the fraction of wet days. So you know the fraction of wet days for a given month. With that, you can derive these two parameters. So that was the nice thing about the Gen and Penning de Vries paper, was that we could access a very simple model for evaluating the transition probabilities. Otherwise, you should take the whole series and do the calculations in the hard way, which means you need to count the number of days followed, wet days followed by dry days, or wet days followed by, and so on. So you could do an explicit calculation of that, but what we do in our case is that we simply apply the equations of Gen and Penning de Vries.
Thank you.
Sure.
Any other questions for Francisco?
And one more question, and I'm done. You are estimating those parameters independently and separately: rainfall, temperature, Tmax, T-minimum radiation. What about the correlation between them? Did you check when there is a rain, you don't have high values of radiation or temperature, etc.? So
no, hold it. But but the simulation of temperature is associated to rainfall.
Okay.
I mean, there is that correlation is taken into account. I mean, This is basically the model of the WGEN, the original model of Richardson that acknowledged the correlation between temperatures and rainfall. And so they are not calculated independently, not at all. In fact, what we have done in ClimaSG is add the correlation between the temperature range and the solar radiation, and that was missing before.
Okay, what about the wind and vapor pressure?
Excuse me?
Wind speed and vapor pressure.
Well, in the case of wind speed, I agree. We are not considering any correlation because, well, when we have tried to find correlations between wind speed and other variables, we have not been successful. So most of the wind speed generation work that I have seen do not consider correlations with other weather variables. In any case, for me, the final thing, I'm not trying to generate wind for, say, energy applications or something like that. What I'm only interested in wind as far as it is a part of the Penman-Monteith equation, and for that, I think it has shown to be good enough. But maybe in some locations, the correlation between wind speed and some specific weather variables might be an important issue.
Thank you, thank you. I will try definitely. Lots of people asking for that kind of generation.
Okay.
Any other questions for Francisco?
Good morning, Francisco. Can
Hello.
you hear me?
Yeah, sure.
Yeah, hi. I'm just curious about how you're calculating your Penman-Monteith ETO.
I'm just using the typical FAO methodology as of the work of Allen et al. I mean the simplest possible approach. I mean,
And-
it's delta RN. Yeah, it's pretty much the same as in the FAO 56 book.
Okay. And so it's grass reference.
Yeah, sure. No, well, for us it's always grass. We are not. We don't follow the alfalfa pathway. We don't consider the alfalfa pathway at all.
Okay,
But
thanks.
in any case, they abandoned the real crop from 56. So grass, now there is no grass at all. ETO is something that doesn't exist, something with an hypothetical canopy resistance of 69 and hypothetical height of 12 centimeters and so on. Yeah.
Yes. Good, thank you.
Sure.
Any other questions? If not, maybe want to do a quick report back as we skipped yesterday.